Hello. In this section, we extend on our goal of conducting hypothesis tests. The difference is that in this one, we're going to be working with situations when we don't know the standard deviation for the population, and also we're dealing with small sample sizes. You'd be working with a t-distribution instead of a normal distribution. So the steps are really going to be the exact same. The only difference is we're not going to be conducting a z-score, we're going to be conducting a t-score. Before we go into a full hypothesis test, if you were to use rejection regions, then you need to be able to find those critical values using t-scores instead of z-scores. So you need to be using not inverse norm, but inverse t. So we're not going to do any hypothesis tests using rejection regions for a t-distribution, but if you did, you would first need to find those critical values. So we're going to just practice finding what those would be. The first thing you need to do is define your level of significance, which inherently is related to your confidence level. Identify the degrees of freedom, which is always one less than the sample size, and then based on whether it's a left-tailed, right-tailed, or two-tailed, calculate your critical values. If you have an older calculator, so a TI-83 or older, you're going to need to be using table 5 in appendix B. I'll show how that works. If you have a TI-84 or newer, the calculator has the built-in inverse t distribution program that you can use. For example, let's say that you wanted to find the critical t score or critical t value for a left-tailed test with a significance level of 0.05 and your sample size is 21. What t-score do you need in order to start finding significant values, unusual results? Well, the degrees of freedom, in this case, are going to be 21 minus 1, which will be 20. And then we need to look at table 5 under the 0.05 significance level for a one-tail test. So we're in the one-tail test, one tail at 5% significance. Our degrees of freedom is 20, and I find where those cross, and I see it's at 1.725. So our critical t is going to be at negative 1.725. If we get anything less than that, then that would result in rejecting the null. You can also do this in the calculator by typing in inverse t. It's always area to the left, 0.05, then degrees of freedom is 20. It will give you negative 1.72. I just didn't from the 5 or go out to the 1,000th place, but it gives the same value. That's if you have a one-tail test. If you have a two-tail test, show how that works. Let's say we have a two-tail test, significance level is 0.10, our sample size is 12, which means our degrees of freedom is 12 minus 1, which would be 11. If you look at table 5, we're going to find the cross-section for a two-tailed at 1 significance level, our degrees of freedom for the 11, where those cross is at 1.796. So if I am to the left of negative 1.796 or to the right of positive 1.796, I'm going to be in the rejection region. If you did this using the calculator, be aware the calculator only does it for areas to the left. If it's a two-tailed test with 10% significance, it means 5% is in each tail. So I would run it with inverse t, 0.05, degrees of freedom is 11, and it gives me that left critical t value, which means I would also know the right by symmetry has to be at positive 1.796. Those are two examples. I'm going to give you a chance to try before we move on to actually conducting a hypothesis test using a t-distribution. So find the critical t value for a right-tailed test, given our significance level is 0.01 and n is equal to 18. Okay, if you use the table, what you would have needed is a one-tailed test, 0.01, and degrees of freedom is 17. We see it's at 2.576. Since it's a right tail, we know you would need to run it with 2.567. If you use inverse t, there's two ways you can do this. Inverse t. You can assume it's a left tail test and then just take the positive. So if we want 0.01 with 17 degrees of freedom, what it would do is it would output for me negative 2.567. Then I would know that I'm really looking for the positive because I'm doing a right tail test. Or you do inverse t with 0.99 with 17, and it would output for you the positive 2.567. Either way you do it's fine. You just have to be able to understand how each one works. That's how you find the critical t-scores or t-values if you were going to be using rejection regions. We're going to be interpreting p-values. So our goal now is to conduct what's called a t-test. It's not a z-test because we are using a t-distribution, because we have unknown standard deviations for the population, and usually small samples is where this will get used. The t-test can be used whenever our population is normally distributed or n is greater than or equal to 30. However, we usually rely on the t-test when the samples are small. So we really need that population to be normally distributed. The test statistic is our sample mean. We're seeing if that is different from the stated mean. And the standardized test statistic is no longer a z-score, but really a t-score. It's found by the same process as before. You'll see it's just the standard deviation is now the standard deviation from the sample. So we need to use a t-distribution because a sample has more variability than if we were assuming we knew that was true for the entire population. Our steps are as follows. They're the exact same steps as before. We're just using t instead of z in step 3, and then doing t-CDF instead of normal CDF. So step 1, verify we can use a t-distribution, state the null and alternative hypothesis, calculate our test statistic, calculate the corresponding p-value, and then interpret our decision, whether we're going to be using a comparison to a confidence or significance level, or if we're going to be interpreting p-values. Example, let's say an industrial company, they are near a river, or what do I say? I think I say maybe a body of water, and they're claiming that the pH in the water nearby, yeah, it is a river, is 6.8. And we're going to see whether that's actually true. So we're going to see if they need to be held accountable. So we randomly select 39 water samples, measure the pH of each. The sample mean and standard deviation are 6.7 and 0.35 respectively. If it's a little lower, it will be, I believe, more acidic, but you'd have to check that. So we're going to see whether the claim made by the industrial company seems to be legitimate. So first off, verify that we can use a t-distribution. The number one reason that we can use a t-distribution would need to be because the population would need to be normally distributed. And in this case, oh no, we have enough samples. So it doesn't state that the population is normally distributed, which is okay, because we have n greater than or equal to 30. If it was less than 30, we would definitely need to have the population be normally distributed. So step 2, state the null and alternative hypothesis. The null hypothesis was that they claimed that it was 6.8. So is equal to 6.8. The alternative is that it's not equal to 6.8. Now we need to conduct or calculate the test statistic. We found from our sample that the sample had an average of 6.7 minus 6.8 divided by the sample standard deviation, which was 0.35, divided by the square root of our sample size. Our sample size was of 39. Top part, negative 0.1. Bottom part, grab calculator, 0.35 divided by square root of 39. We get 0.056. Divide the top by the bottom, and you end up getting a test statistic of negative 1.79. Now we need to find the corresponding probability. So I need to determine the p-value using, just got jumbled, there we go. Using t-CDF, lower and the upper. Our p-value, though, recall this is going to be a two-tailed test. So I need to find the probability of being less than negative 1.79 or bigger than 1.79, because it didn't specify direction in the first, so it could be one or the other. So I'm going to need to double whatever I find here. So t-CDF, I'll do the lower one, negative 1,000. Up to negative 1.79 degrees of freedom. There were 39 in my sample, so 38 degrees of freedom. Grab a calculator and run it. So t-CDF lower is fine. Upper was negative 1.79. Degrees of freedom was 38, I believe. Let's check it. Yep. And then tells me we get a p-value 0.04. If I double that, that will be, well, so that's just half of it, 0.04. The whole p-value would be 2 times 0.04, 0.08. If I look, this was asking me to see if there's enough evidence to reject the company's claim at the 0.05 significance level. If I'm using it and comparing it to a significance level, we are not going to have enough evidence. So I would say with a p-value of 0.08, well, if I was using the interpretation like I would say that we should start to use, we would say that there is weak evidence to reject the company's claim that the pH level is 6.8. So it looks like the company's claim is going to stand for now. If you were comparing it to the confidence level, we would say that we don't have enough evidence to reject. So the null stands for now. You could also run this whole test in the calculator. You go to Stat, tab over to Tests, run a t-test. I'll show where you get that stat. Over to Tests. You're not going to run a z-test, you run a t-test. The screen will look like this. Make sure you've chosen stats. You enter the claim from the null hypothesis. You enter your sample mean. You enter the sample standard deviation. Sample size of 39. We are checking whether it was not equal to the stated mean. And then you hit calculate, and there's a result page. There's our p-value 0.08. And I would say this. So on the homework, I recommend doing 1 by showing all the 5 steps that we just did prior, because there's a chance I would ask you to do that on a quiz. Otherwise, you can use technology for the rest, but just be sure to identify all the inputs you supplied in the calculator, which is essentially write down that if you're going to use the t-test built into the calculator. We're going to do one more, and we're going to do it using technology. So a government agency is investigating the effect that drinking has on one's reaction time while driving. The initial claim is that one's reaction time is the same while sober and after consuming 2 beers, so the mean difference is 0. To test this, a study involving 32 drivers was conducted and found the mean reactionary time increased to 0.5 seconds with a standard deviation of 0.8 seconds. Find and interpret the p-value for the claim there is no difference. So verify that we can use a t-distribution. Well, we had 32 drivers, so n is greater than or equal to 30. State the 2 hypotheses. The first hypothesis would be that it's less than or equal to 0. Really, it's the equal to 0 parts. The alternative is that it's more than 0. It increases the reaction time, which is the delay. Then we're going to use a t-test on the calculator. So I go to the t-test. The null hypothesis was a mean of 0. Our sample found that the reaction time was 0.5. Is that enough? Is that significantly different? The sample had a standard deviation of 0.8. Our sample size was 32, and our test is a right-tailed test because we're checking to see if it increased the reaction time. So it's a right-tailed, it's greater than. Our corresponding p-value is 6.5 times 10 to the negative 4. That is 0.00065. So with a p-value of 0.00065, there is very strong evidence to reject the claim that the difference in reaction time is 0, and we can even say more. And in favor of supporting the alternative that the reaction time increases. If there truly was no difference in reaction time, then there's only a, what is that, 0.07% chance we would have got the results that we did. So highly unlikely, which means that it's probably the case that there is a difference in the reaction times.